The title of the second talk is Machine Learning in Financial Markets, Pitfalls and Solutions. Serena is a senior data scientist at Delphia, where she works on combining public opinion and social media data to drive stock market predictions. She previously worked at Mercatus Technologies, where she specialized in using machine learning to personalize the online grocery shopping experience and built the company's first recommender system. Serena organizes the founder stream of ACE, a machine learning community started here in Toronto. They have also lots of events, if you look at their website. And she leads diversity and inclusion initiatives for the group as well. Serena holds a Master of Science in Mathematics from the Hong Kong University of Science and Technology and the Bachelor of Science in Mathematics and Biology from McGill University. Thank you very much, Serena, for joining us tonight. Feel free to start your presentation.
Okay, sounds good. Yeah, first of all, thanks, Drago, so much for having me. So hello, everybody. I'm Serena. So today I'll be talking to you about using machine learning in finance, and I'll be presenting some pitfalls and also some solutions. So first, Dragos did introduce me, but I'll reiterate a bit about who I am. So I'm a senior data scientist at Delphia. So we are a fintech company here in Toronto, and we're building an investment collective that will let you or anybody invest in the stock market with your data. And specifically, as mentioned, I work on combining public opinion and social media data to create investment insights and also trading strategies that will benefit the collective. And I am the stream owner for the Founders stream, but also a new stream called the Algorithmic Inclusion stream at ACE. So again, as mentioned, ACE is a community of machine learning practitioners and enthusiasts based here in Toronto, but we are now global. We have members from all over the world. And we're currently working on creating a repository of machine learning research videos by inviting authors to present their work over live streams. So we also have socials where community members present their projects or papers they've read. And it's a really great way to stay up to date with the field, make friends. And when we can get together all in person, we like to eat free food together. So if you're interested in joining, please let me know. We would definitely love to have you. In particular, since I'm in charge of diversity and inclusion initiatives, any women, I'm always happy for more women to join. And we have a women-focused event called Women in AI on June 9th, and it's online, and everybody is welcome to join. It'll be a celebration of technical achievements of women in our community, and we'll also have breakout sessions for networking. And you can find the event online at Eventbrite. So again, I also have an undergrad in math and bio from McGill. I have a master's in math from the Hong Kong University of Science and Technology, specifically focused on fluid dynamics. A bit more on the personal side, I love playing soccer, I love cycling around the city. I think it's a great way to get around, and even in the winter. Okay, so I'd like to share a bit more about my background and what I've worked on, just so you can understand my perspective, because I think it's really important to highlight that everybody's background is unique, and as a result, everybody's take on problems is unique, and I think that's great. So in particular, I have a background in math and biology through my education, finance through internships, my current work, and also personal interest. And interestingly, fluid dynamics and oceanography, which I studied in my master's, they do relate to finance, as I realized during my studies, but that's the subject of another talk. And finally, I have experience in recommender systems, and I'm hoping to publish my first paper on session-based recommendation this year. Okay, so we're all here because of AI geeks. So let's just start off by answering this question, what is AI? So I'm sure many of you have your ideas on what AI is, but I do have a bit of a hot take. So first, let's just see what the internet says. So personally, when I was starting out as a data scientist, fresh out of my master's, I wanted to know what the definition really was of AI. And naturally, I looked to Google, and I think it's a pretty reasonable place to start. So Google says that AI is intelligence demonstrated by machines in contrast to the natural intelligence displayed by humans. And I think this is a fine definition, but I do disagree with its widespread usage and the widespread usage of AI. And I would say I disagree on the basis that this definition doesn't take into account what AI really is at the core. It's just machine learning oftentimes, also reinforcement learning, but really to get more atomic, it's just math. So AI is just math. And I really find that it's a lot less scary when you describe it as just mathematics. And I would rather AI be defined as the application of mathematical models to perform human tasks previously believed to be accessible to only humans. And my reformulation might be very similar to Wikipedia's definition, but I really just think it's worth highlighting that AI is math. It is accessible. You can learn AI methods if you work hard and if you study it. So it's not something scary. So while I do prefer to use terms such as machine learning rather than AI, I do accept that AI is becoming much more widespread, but I just really want to emphasize, please don't be deterred by it or put these methods on a pedestal as well. And in the spirit of this meeting or meetup being AI geeks, I will use the term AI throughout this presentation. Okay, so now that I've had a bit of time to explain my views on AI and the term, let's just talk about an example of what AI can do, because there certainly are some incredible use cases. So one fairly recent development in natural language programming, or processing, I should say, is the development of transformers, which at a high level, transformers are a language model, or it's a, I guess, family of language models now that models the interdependency between words and sentences. And if you train this sort of transformer model on a large text corpus, it yields some very fascinating results. For example, language generation. So you can actually play with a trained transformer model on a site called Talk to Transformer. So as seen here, given a prompt, you can create a paragraph that's actually very close to what a human might say. So what I've done here is I've given the prompt, "Thank you, Dragos, for inviting me to present." And then the model has taken that prompt and generated some text that says that I'm currently in my freshman year and that I enjoy challenging math and I'm working hard to get as good at STEM as I can. And I also like biology. I think it's kind of funny because it did end up describing me a little bit. And I think a natural question might be then, if machine learning is able to generate coherent text, can it be used to predict the stock market? Because language generation is very hard and stocks are also hard to predict. So then you might be thinking, why not jump from one domain to another? But this is actually very idealistic, and this brings us to the focus of the talk. So essentially today I will really just be talking to you about why domain knowledge is very important. And when tackling a problem using machine learning, it's important to be mindful of the domain in which the problem lies. So in the talk, I will outline 3 problems that might occur if you try to sort of blindly apply machine learning to financial markets without taking special consideration of the idiosyncrasies of the field. So I'll outline each problem using the framing of what a machine learning practitioner might be tempted to do, why they may run into a problem doing that, and what they should consider doing instead. And I'll use examples inspired by my work at Delphia where I can. Okay, so the first problem in financial markets is that the past does not equal the future. And of course, this might seem obvious, but please hear me out. So in machine learning, the past is often indicative of the future. So let's take a computer vision standpoint for this example. So a dog will always be a dog. And by the way, this is my dog Pixie. She's very cute. So a computer vision practitioner who has a highly accurate model that can classify dogs from fish, they can be very happy with their work because dogs are not going to morph into dog-fish hybrids anytime soon. So they can be confident that their model is a good one. And really what I'm saying with this analogy is that what happens in the training data oftentimes is fairly indicative of what might happen in the future. And in that sense, the past does equal the future. And as I said, a dog will always be a dog. And I see I'm already getting a lot of questions, which I'll get to later. So that was the computer vision example, or a computer vision example. But then you might be asking, how does this apply to financial markets? So the problem in taking this approach in financial markets is that truly the past does not equal the future. So what happened last week might not help you predict what will happen next week. And on top of that, you have to be aware of the possibility of what's called black swan events. For example, coronavirus. So these are events that come as a major surprise and their impact couldn't have been predicted. And there really are a lot of unknowns in financial markets. So a model that's trained perfectly to fit your in-sample data or your training data, that doesn't mean that your model will generalize to what will happen in the future. And even if your model does fit your out-of-sample or your test data, that really doesn't mean it'll help predict future stock price movements. So for example, we can consider Tesla. So in February 2020, very recently, sort of before coronavirus really hit North America, the stock price experienced a huge run-up, which you might recall. And let's specifically consider this time series of Tesla stock. Here we have it pictured from February 2015 to about 5 months ago. And a reasonable forecasting approach, if we wanted to forecast into February 2020, it could be quite reasonable to just extrapolate the trend and the time series from what's happened in the past. And that might look like this. And it looks like it fits quite well, and it's a very reasonable approximation of what we think might happen in the future. But in reality, this is what happens, and you can see there's a huge difference in what we thought was going to happen and what actually happened. And Tesla stock, it went up about 5.5 times in the few months leading up to February 2020. So really what happened in Tesla's past from February 2015 was not indicative of what happened in February 2020. Okay, so then you might be asking, how do you solve this? What's a machine learning practitioner to do? So we have our own perspective on this problem at Delphia, and the approach we like to consider is, first of all, using a linear model, so a general model. It's often better to use a simple model as it's much more generalizable and more robust to these black swan sort of unforeseen events that might occur. So I would urge you to fight the urge to use deep learning right away. Deep learning is great, but it's not necessarily the solution for every single problem. And I'm a huge fan of Occam's razor, which says the simplest solution is often the best solution. So the first thing you can consider is using a linear model. And another approach that we've considered at Delphia, and we find it quite interesting, but we haven't yet implemented, is the idea of simulating data. So rather than testing on real data, the idea would be to project synthetic paths into the future to represent all possible versions of the future that could occur. And then the idea would be to choose a model that best generalizes across all these possible paths. And this best generalizing model may very well be a linear model. Finally, another approach that we like to take at Delphia is to not take our backtest results so seriously, and a backtest is just seeing how well a strategy or a model would have done on historical data. And I think this idea of taking things, with a grain of salt and not so seriously, I think it's a good motto for life in general as well. So that is the first point. Now on to the next. Okay, so the next point is that perfect accuracy in financial markets is not enough. So we'll continue with our example of a computer vision practitioner who has developed a model that classifies dogs from fish. So let's say that they've achieved 99% accuracy with their desired accuracy metrics. And they may be tempted at that point to dust their hands off and call it a day and say, great, my model is awesome. Of course, there's always going to be issues of model drift, but that's besides the point here. So a computer vision practitioner, they have their highly accurate model, and this is what they're used to. And when they're presented with a stock market prediction problem, they might think that once they've developed a model that predicts the stock market accurately, then they're done. But really, that isn't enough. So even if you could perfectly predict where stock prices will go, there are important parameters that you need to determine beyond this. So for example, how often will you buy or will you sell? Will you go long, that is bet on stock prices increasing, or will you short stocks, that is bet on stock prices decreasing? And when you do buy or you do sell, what is your bet size? So how much money do you put into one position? And how long will you hold for? And how many stocks will you have in your portfolio? How will you account for things like slippage? So changing the value of even one of these parameters will change the outcome of your trading strategy. And it can be the difference between making a lot of money or losing a lot of money. And of course, you never want to be one to lose. So at Delphia, we take this approach of splitting our trading strategies into two parts. So first, there's the development of the signal model. So that is developing some sort of machine learning model to predict the movements of the stock market. So an example signal model using the example of Tesla might be that, let's say that we've noticed that every time Elon Musk tweets something positive or something with a positive sentiment, Tesla stock then goes up. So we may use a machine learning model to label the sentiment of Elon Musk's tweets, and then we would continuously run his tweets through this model in order to determine if there is a strong signal or a strong indication that Tesla stock will go up. And then we have our signal, and that's great. But the next part of the trading strategy problem is to develop what we call the strategy model. So this strategy model looks at how we can incorporate this signal or translate it into trading actions. So we would investigate various strategy parameters. Again, those would be parameters such as how long we would hold our positions for, how much money we use each time we trade, the number of stocks in our portfolio, etc. So the problem here is that if you come from a traditional machine learning background, that is, let's just say a background that's not financial markets, you might think that your job is done once you've developed an awesome signal model, but in reality, that does equate to solving only half the problem. Okay, so that was the second point. Perfect accuracy is not enough. And now we'll move on to the third point, which is that memory is important. So this next point, and actually quite a bit of this talk, is inspired by a book called The Advances in Financial Machine Learning by Marco Lopez de Prado. So Lopez de Prado, he's a very well-regarded figure in the field of financial mathematics. He holds 2 PhDs. One is in mathematical finance and one is in financial mathematics, which I think is very interesting and very specialized. And I highly encourage you to read some of his books, or read this book if you're interested in learning more about pitfalls and solutions in using machine learning in finance. Okay, so first I will give you all a quick primer on differencing time series. So stock market prices are time series. That is, every stock price is presented as a point in time, or it's presented, sorry, with a point in time at which this price occurred. So stock prices are made up of price timestamp pairs. So first we need to talk about what a stationary time series is. So a stationary time series is one whose distribution does not change over time. So to put that another way, its mean and variance may be the same regardless of what point in time you're considering. And many time series models do assume that data is stationary, and that's because the time series models assume that the underlying data generation process remains constant throughout time. And really all models have assumptions, and stationarity is an assumption for many time series models. So then, given that we have time series stock data and we need to make it stationary, but let's say this time series stock data originally is non-stationary, then we can do what's called differencing. So in differencing, you compute the difference between consecutive observations. Specifically, this is called integer differencing. And then the resulting time series, the one that is differenced, it's stationary. So that's differencing. And another concept is memory. So you can think of memory, or you can think of, let's say, a time series has memory when its past values are related to its future values. That is, it has a trend. And put another way, a time series has memory if its previous time steps are predictive of its future values. So those are 3 important terms to keep in mind. So stationarity, differencing, and also memory. Okay. So as mentioned, stock price is a time series. And when working with stock price data, one of the first things a highly trained data scientist or machine learning practitioner or mathematician might do is to difference it to make it stationary. And this really is regarded as one of the first steps to take. And why is that? Well, because as mentioned, every model comes with its own assumptions, and time series models such as ARIMAs, which stands for Autoregressive Integrative Moving Average, these models assume that the data you're working with is stationary. And then again, to reiterate, what does the stationarity of a time series mean? So again, its distribution doesn't change over time. The mean and variance do not change over time. So taking a look at the time series on the left, I hope you can see my mouse. So the mean from time step 0 to 20 is about -1, but then if you look at the mean from, let's say, time step 40 to 60, it looks more around 0.2. So that's not stationary. And as mentioned, we can integer difference the time series by subtracting the previous time step value from the current time step throughout the entire series. And that results in the plot on the right. So you can see that mean does stay around 0. So it's great. And that means that we can apply a time series model like an ARIMA and be well on our way to predicting stock prices. But at this point, I would say not so fast. You're sort of falling into a pitfall. There's a bit of a problem in this approach. And by differencing a time series, we are effectively removing memory. So then we are removing any information in the time series that may have predictive power. And that's why the title of this section is called Memory is Important, because it is. So on the left, in the non-stationary time series, if we were to extrapolate, let's say, the time series from time step 20 to 30, we would just fit a regression and end up predicting fairly well the value that occurs at time step 40. And this is because this non-stationary time series does have memory. And on the right, the time series, it does look, I mean, you could say it looks like a bit random. And that's because we've inadvertently stripped out any memory. And I think this brings up a very interesting problem. So first, if we consider that the efficient market hypothesis holds, that is, anything that could affect stock prices is already priced into the market, and markets as a result cannot be beat. So put another way, the efficient market hypothesis says that markets cannot be predicted. And when we're working with stock market data, when we difference our time series using integer differencing, we end up removing any memory. So past prices cannot be effectively related to future prices. So then what we're doing is we're creating an environment where the efficient market hypothesis holds really by construction. As mentioned, the hypothesis says that markets can't be predicted, but we're integer differencing our time series so much that markets in effect can't be predicted. So it is a bit of a strange situation. So then what is a well-trained data scientist supposed to do? If we're stripping away memory, that's very useful from stock market data by doing integer differencing, but then we need stationarity in order to use our models. What solution is out there? So I kept on mentioning specifically integer differencing. And again, that's when you subtract, or when you take the value of your time series today, subtract yesterday's value, and you do that for every step or every day in the time series. Well, the solution here is to not use integer differencing. There's something that's called fractional differencing, and the math is a little complicated, but at a high level, this distinction is as follows. So in integer differencing, you compute the difference between time steps, and those time steps will be an integer apart. So for example, if you want to do first order differencing, you compute the difference between the current time step and the previous time step as mentioned. For fractional differencing, you don't subtract values from a time step that's an integer value apart. To be a bit more concrete, instead of subtracting yesterday's value, you would subtract something a bit smaller than yesterday's value. And what you end up getting is a time series that is stationary, but still actually retains a bit of memory. So you can see an example of the fractional difference time series on the right-hand side of the slide. And as you see, we can still capture this large peak and drop off at around time step 80. So we've retained a bit of memory, but when you do statistical tests for stationarity, such as the augmented Dickey-Fuller test, you can see that the time series is in fact stationary. So then at this point, a data scientist could go on and be really happy to use their favorite time series models. And the main takeaway here is that if you can achieve stationarity that doesn't come at the cost of memory, then why not? Okay, so in summary, when applying machine learning to financial markets, just remember that domain knowledge is important. And while machine learning for stock market prediction might sound quite feasible, it actually is quite hard. And this is threefold, and three of the reasons I've highlighted today are that the past does not equal the future, perfect accuracy is not enough, and also when dealing with stationarity and memory, it's a trade-off. So thank you. Okay, I had any questions? Let me go and take a look at the questions. Maybe should I stop sharing? Stop sharing for now. Okay. Any questions? Oh, I see one. Yeah, so Voy asks, great, well, he says, or you say great talk, sorry, I said you said great talk, thank you so much. Yeah, so these three examples definitely are not exhaustive, and I would suggest if you want to learn more about pitfalls, you should check out Marco Lopez de Prado's book on advances in financial machine learning. It's really interesting. It's about 14 chapters, and every chapter highlights a few pitfalls in each one. And if you want to maybe save a bit of time and be a bit lazy, you can also Google the name of the book. And there are now a lot of Medium articles and other resources online that highlight the pitfalls. Okay, okay, I'll follow up with Boy's question. So do you think the book is for everyone? Many people say it is quite advanced. What other book could you recommend? Yeah, it is a fairly advanced book, and I think I would recommend then instead reading some of the blog posts that have been written about it. In terms of another book to recommend, I'm really not too sure because that's the first one that I've encountered that brings up these sorts of ideas, and I think Marco Lopez de Prado is a bit I guess, controversial with his views in the field. He doesn't hold the same views as everybody else does, so he is a bit unique. Okay, I'm just going to mark these as done. Okay. Okay. So Salim asks, what are some of the helpful machine learning techniques that are used in finance, and does it include reinforcement learning? So that's a great question. So using reinforcement learning for finance, I have seen it being done for portfolio optimization and also for stock market prediction in general. It isn't something that I've looked into much myself, but it's actually on my to-do list in the very near future. I'm currently reading the reinforcement learning book by Sutton and Barton, which is one of the sort of foundational reinforcement learning books. So there's that. In terms of other helpful machine learning techniques, I would say surprisingly simple models, as I mentioned, linear models are very widely used, mainly because they are so well able to generalize across many different paths of what might actually happen with stock market data. So while it is very tempting to use complicated models such as a transformer for finance, as I mentioned, I think it's good to sort of start simple. That being said, using more complex models can be useful in the parts of finance that involve text. So for example, parsing earnings call transcripts, using a transformer for that could be very useful to detect sort of sentiment and also maybe, I guess, lying, if that's the right way to say it. Because sometimes maybe executives will say one thing but really mean another. Okay. Taking a look at more. Okay, Russell says, this is a great presentation. Thank you so much about the efficient market hypothesis and AI. Does AI prediction give better price estimation than the last observed price? That's a good question. I would say, so you could be using machine learning or an AI technique to predict stock prices. I would say the further back in time, or sort of the further into the future you would like to make your prediction, the worse your model is going to be. And I think using the last observed prices, it's quite good. It's very simple, but it's very good, but it's not going to help you predict stock price, 3 months down the line or a year down the line. That's a good question. Okay. Nicole asks, says, thank you so much for the talk. Thank you. I'm glad you liked it. Is this concept currently being used and applicable for asset and private equity management and finance? That is very interesting. So I don't know too much about private equity, but I was reading recently I was reading an investment banking textbook that was talking about when you are valuing companies, for example, a company that might IPO or a company that might undergo an acquisition. And one method for valuing, so I know there are like 3 main methods. One method is, what is it called? Comparable transaction analysis, something like that, or comparable company analysis, precedent transaction analysis, and then discounted cash flow analysis. And I found it very interesting because in comparable company analysis, you're essentially looking at companies that are very similar to the company that's going to be undergoing an acquisition or the company that's going to be IPOing. And you look for companies that are quite similar to it, so a comparable universe of companies, and then you base your valuation of your target company based on the valuation of those comparables. And I did some research to see if any machine learning methods had been used to create this universe of comparable companies. And I was surprised to see that there was only one article by Morningstar saying that they were using machine learning in order to identify a comparable universe of companies. And to me, that says that either these methods have not yet made it to finance to that part of finance, or it means that investment bankers would like to continue using their methods that have always been sort of tried and true, or it means that machine learning is being used everywhere in asset management, private equity management, but it might just mean that companies are very secretive about it, because firms often are very secretive. So I feel like that was a bit of a non-answer, but I hope that still was interesting, and I'm happy to chat about it too offline. Okay, more questions. So let's see. Christina says, on the opposite side of pitfalls, what are some examples of successful use of machine learning in financial markets? Well, one example, as mentioned, is using machine learning to parse earnings call transcripts. I think that's been done really well. And if you think of it, you can use a machine learning model and just pass through an earnings call transcript, and it's very fast and you can do it at scale. And yeah, I think that earnings call, and like I said, anything that's text-based, you can use machine learning for that, but it's really not, it is financial markets in that the results and the outputs of those models can then be fed into other models to then predict stock price, but it's not pure stock price prediction, in a sense, using the time series to derive your insights. Okay, let's see. Okay, Nicole asks, I want to learn more about machine learning and AI for financial markets. Would you be able to recommend books or other resources? Yeah, it's a good question. So I think that the best way to start is getting a good handle on machine learning in general. So my favorite book is The Elements of Statistical Learning. It's a classic. And then from there, I would say, well, financial markets and finance in general, it's so broad. So I would suggest that you figure out what area of finance that you're most interested in. And then actually, rather than reading machine learning textbooks that talk about finance, I would suggest reading textbooks that are actually just finance, and then thinking about how you can apply machine learning there to solve these problems with your unique perspective that maybe other people haven't thought of. And then in terms of books that I can suggest for finance, one book is called Options, Futures, and Other Derivatives, which is supposed to be one of the sort of Bibles of finance. So that's a good one. Okay. Voy asks again, Voy, you're asking lots of questions. It's great. So seeing as there are so many competitors in algo trading these days, how does Delphia differ? Is there anything that you do very differently to everyone else? Yeah, that's a very good question. So I think everyone at Delphia will be really happy for me saying this. So Delphia is an investment collective. So the idea is that rather than being a company, let's say Google, any sort of big tech company or any big company with a product, we're not in the business of taking your data and making money for ourselves. What we have is we have a product where you can connect your data sources. So you can connect your social media data. You can answer surveys through our app, for example. This is the general idea. And with this data, we can then use it to create better investment strategies because we have this source of alternative data. And the whole idea is that we then compensate you for your data. So if you are someone who maybe doesn't have the funds to invest in the stock market, then by connecting your data, we can actually pay you a bit of money and you can invest that money with us and we can manage it for you. So in that sense, we're trying to take a more ethical approach and reduce the wealth gap as well. Okay. In addition to day trading, are there any methods using market fundamentals for long-term investing? So do you mean market fundamentals as in, okay, well, I guess I don't know if you can clarify. So I'm not sure if you mean, Salim, market fundamentals as in like fundamentals about companies, for example, a company's PE ratio or something else. From my understanding, using fundamentals, that does lend itself to a more long-term method. So for example, you might be a value investor and you buy for the long term, or you might be a growth investor and you buy these companies that have a PE ratio that lends itself to growth, and you just take it more on a long-term side. And personally, with my own investing, I do try to take a more Warren Buffett long-term approach. Although Warren Buffett did recently lose quite a bit of money, so that's a bit unfortunate. Okay, Carlo says, have you used LSTM models for predicting stock prices? Are they better than ARIMA and SERIMA? That's a good question. So, I don't know if I can conclusively say that in my experience, LSTMs are better than ARIMAs or SERIMAs. In my work at Delphia, we've worked more with ARIMAs and also SERIMAs because of the background of the team. And when I have compared the results of LSTMs and ARIMAs side by side, it's been fairly the same. And then my argument then would be that I do think that ARIMAs are simpler models, and I think it's always best to go for a simpler solution, at least at the beginning. Okay, Amit asks, what are some of the information sources you take into account for a predictive model? Does it include mostly news? This might be dumb. Oh, I don't think it's a dumb question, but are predictions mostly based on previous prices only? Yeah, I think it's a good question. So essentially, I think you're asking about alternative data. So yeah, news is a great source for alternative or of data. I would say alternative, in terms of being alternative, I think news is used so much, it's sort of less alternative than it used to be. Other examples of alternative data, at least what we're collecting at Delphia, is social media data, Amazon purchase history, Uber ride history, Lyft ride history. And there's also a lot of really interesting use cases. So for example, if you're interested in learning more, you could check out Quandl. So they're a local company in Toronto, and they are an alternative data provider, and they have partnerships with different companies who will provide their data, their alternative data source to Quandl. Quandl will package it up and then sell it to hedge funds, I believe. And they have one interesting story about looking at insurance filings for cars, new cars. Specifically, I don't know how they connected it to Tesla, but what they ended up determining was they were able to predict Tesla's new car sales before anybody else because they were looking at insurance filings. So that's a really interesting example of a use of alternative data that definitely led into an earnings prediction model. And I'm sure whichever hedge fund bought that data was probably pretty happy with that. Okay, Hannah asks, is it necessary to learn Python to start learning AI? No, I don't think so. So you can start with learning the math part first and sort of like take a more theoretical approach to start. In terms of Python, well, there's a lot of different languages nowadays. So Python is definitely great. I would say it's probably the one that you will see the most in tutorials and advertised as sort of the language that employers ask for. But R is also really great. R has great statistical packages. For example, implementing an ARIMA or a Serena model in R is very simple and perhaps a little bit more complicated in Python. So my answer would be no, it's not necessary to learn Python to start learning AI. Okay, Paul says, any attempts in industries on using chess-playing models to predict stock prices, perhaps basing on combinations of candlestick patterns to predict next movements? Just a wild guess. Yeah, it's a good question too. I mean, so reinforcement learning is it's a chess-playing model. And I think, as mentioned, yeah, reinforcement learning in finance is something that I haven't had a chance to look into, but I'm sure researchers have been looking into it. And I think another interesting idea, not necessarily chess-playing models, but is the idea of using computer vision models to sort of classify candlestick patterns and then predict next stock price moves. Okay, Voy asks, how can we get in touch with you later for some follow-up questions? So you can feel free to add me on LinkedIn. If you search Serena McDonnell, I should come up. And yeah, just message me, connect, I'd be happy to chat. Okay, another question. Oh, this looks like a good one. So with the current economic environment, does the data collected now not break the models and create an inability to provide learnings for today and tomorrow till the economic situation reasonably stabilizes? Yeah, this is a great question. That's not just a problem in finance, but it's a problem everywhere. And I think an example that a lot of people could relate to is grocery. So people, and that's where I worked previously at a software as a service company for groceries. That is my background. So people are panic buying, people are buying more toilet paper than before. And if you have, for example, a lot of recommender systems in grocery, they are popularity-based models. So they will recommend the most popular product, and they might recommend the most popular product over your lifetime as a shopper. If somebody has purchased 100 rolls of toilet paper, but previously they purchased one bunch of bananas a day, they're going to continuously be getting toilet paper recommended to them rather than bananas, which truly is what is their preference because they buy it more frequently. Anyways, so the point is that this is something that's being actively looked into. I know folks over at different grocery companies, they are trying to decide if they should sort of throw out all of their data and only use data from March and onwards, or should they, in the future, once this is all over, just then throw out the data from March until this is all over. So it's a very difficult question, and I think we'll probably see a lot of research being done on it. Fortunately for Delphia, since we're a startup, we're more in the preliminary stages, so that's not something that we need to worry about now, but I think it's something that we definitely will need to worry about in the future. Okay, another question. Post the signal model where the ML models are trained in the strategy model. Is the focus on quantitative day trading or long-term investing? Okay, so to reiterate, I think Sandeep was asking about the strategy model. So when you build a strategy model, is it more on day trading or long-term investing? So that would be a strategy parameter that you would define. So you can define your strategy to be in the short term, or you can define it to be in the long term. So really up to you. Okay, I think those are all the questions. So if anybody has other questions, definitely feel free to reach out on LinkedIn. And yeah, thanks so much for having me.
Thank you, Serena. Very interesting presentation.